Dear students, let us begin today's lecture as our tutorial lecture first. We'll take up a few exercises and then we'll continue with our discussion. So find out the Spearman rank order correlation coefficient between the two given lists. L1, 1, 2, 3, 4, 5, 6 and L1 is equal to 6, 3, 4. So they are partial lists in that sense because the documents that are listed there are not completely overlapping. So for converting the partial list into a full list, use reverse ranking method and number two, average ranking method. So this is the exercise that let us take it up first. Okay. So this is part number 1. I have got L1 as 1, 2, 3, 4, 5, 6 and L2 as 6, 3, 4. So I've drawn a line here. This is the line that I've drawn. Now besides beyond this point, I'll have to complete this partial list. 6, 3, 4, I'll have to complete. So using reverse ranking methods, what I'll do is that what all documents are remaining, I'll just list them in a reverse order so as to penalize the search engine for giving extra documents, right? So 5, 2, 1, because they were the ones which were remaining. So I listed them in the reverse order 5, 2, 1, right? So now finding out Spearman rank order correlation coefficient, first I'll have to find out mod di. I'm writing mod di so that I don't have to write the sign over here plus minus sign. Otherwise di square will be same for mod di or di, whatever. Di square will be the same, right? So 1 minus 6, 5, 2 minus 3, 1, 1 minus 5 is 1, mod when I'm saying 5 minus 2, 3, 6 minus 1 is 5. So I squared them. 25, 1, 1, 1, 3 square 9, 5 square 25, total is 62. I just substitute in the formula 1 minus 6 summation. So summation is 62. The summation will come here upon n into n square minus 1. So 6 into 36 minus 1. So this comes out to be minus 0.77. If I repeat the same exercise by taking the conversion of partial list into a full list using average ranking method, then in that case, how will it differ? 1, 2, 3 is there, 6, 3, 4 is there. So now these remaining ranks, what I'll do is I'll take the average of them. Assuming that the documents which are not at all touched by the user are actually at the same tied spot. They are tied up for the same place. So the remaining were 4, 5, 6. When I took the average, so I'll say that all of them are at 5th position only. Now over here it becomes immaterial whether I write it as 1, 2, 5 or I write it as 5, 2, 1 or I write as 2, 1, 5, whatever order, because the difference, the sum of difference will remain the same. So again 1 minus 6 is 5, 2 minus 3 is 1, 3 minus 4 is 1. Now 5 minus 1 is 4, 5 minus 2 is 3, 5 minus 5 is 0. Squared them, 25, 1, 1, 4 square 16, 3 square 9, 0, 52. Just substitute in the formula 1 minus 6 into this summation. This summation will come here upon n into n square minus 1. So this comes out to be minus 0.486, which is less negative than minus 0.77. So reverse ranking method is more harsh penalization. So this gives you two practices. Firstly, how to calculate the Spearman rank order correlation coefficient. And secondly, how to convert a partial list into a full list, a partial list into a full list using either of the two methods, reverse ranking or average ranking method. So now let me move on to the next exercise. Evaluate at least half of 0.6, 0.3, 0.7, 0.1, 0.0, 0.4 using ordered weighted averaging. So first of all, I have to see what is my M. What are the number of elements here? So 1, 2, 3, 4, 5, 6. So it is I varying from 0 to 6. And then I by M is 0 by 6, 1 by 6, 2 by 6, 3 by 6, 6 by 6, which is 1. So now Qi by M. I'm talking about at least half. So at least half is this one, right? This is at least half. 0.5 and this is 0, right? And this is 1, right? So I by m is 0 anyway. This is 0. And then this point I get into the linear range straight away. So it is 0.167 minus 0 upon 0.5 minus 0. So this comes out to be 0.33. 2 by 6, I'm still in the linear range because this is less than 0.5. So it is 0.33 minus 0 upon 0.5. So again comes out to be 0.33. Now 0.5 is 1. Okay. So either way it will come out to be 1, whether you put it in the formula or we know that 0.5 onwards it is 1 anyway. Okay. So it is 1. So this is about q by m, and for all the remaining places it will be 1 1 1. This is equal to this will be 1 1 1 because I have crossed the limit of 0.5. So I'm got into the 1 range. So now wi, my wi will be this minus this, which is 0.33, this minus this, which is again 0.33, and this minus this is again 0.33 or 0.34, because summation of them should be 1. So I'm making one of them as 0.34. Now 1 minus 1 is 0, 1 minus 1 is 0, 1 minus 1 is 0. So I get these 3 weights, W1, W2, W3. So in order to find out at least half of this, I should multiply W1 with the largest. So 0.33 into the largest is 0.7. Then again 0.33, this 0.33 into second largest, which is 0.6. And then 0.34, which is this one, 0.34 into third largest. Okay, so this is third largest. And then from there on, 0 into fourth largest plus 0 into fifth largest plus 0 into sixth largest, or all of them will be 0. So when I calculate this, it comes out to be 0.561, right? I have simply 0.33. You can do an exact calculation also. I've done an approximate calculation. So taking 0.33 outside, it will be 0.7 plus 0.6 plus 0.4 inside. So that is how I'll get the result of at least half of the given value. Okay, so this also gives us the practice of how to find out ordered weighted averaging for a given number of criteria, given number of elements, right? So let me move on to the next exercise now. Find out the fuzzy preference relations RV from the user preference ordering given by the sequence vector V is equal to 5, 1, 6, 3, 2, 4. What does it mean? That fifth document was clicked first, first document was clicked second, sixth document was clicked at third position, third was clicked position, second document was clicked at fifth position, and fourth document. So now the fuzzy preference relation, we know that this is the formula. RVIJ is equal to half 1 plus Vj minus Vi upon n minus 1, right? So how can I find out RV12? Diagonal elements will be 0.5, 0.5, 0.5. We all know that, right? Because whenever I and j are equal, so Vj minus Vi will be equal. So this term will be, so into 0 will be half, which is 0.5. So even using the formula, the diagonal elements will come out to be 0.5. Now RV12 is half 1 plus. Now I have to see where does the second document result. So the second document is at fifth position. You see, second document is at fifth position. So 5 minus 2 upon 6 minus 1, which is 0.8. 5 minus 2, why 2? Because the first document is at second position, right? So this basically means preference of first document over second document. So this comes out to be 1 plus 5 minus 2 upon 6 minus 1, which is 0.8. So 0.8. Now 1 minus 3 likewise, sorry, RV13. So it is 4 minus 2. Why 4 minus 2? Because third document is at fourth position and first document is at second position. So this comes out to be 0.7, right? RV14, 3 minus 2 by 5, because fourth document must be at third position. Just hold on. 4-1, right? Just hold on. There seems to be some error. Fourth document is a sixth position. Fourth document is at sixth position, and first document is at third position. Okay, so there may be error, but then this is how you go on computing all the values. If there are any errors, you can just correct them, right? And you will see that 5-4. Let me see 5-4. The farthest are 5-4. So let us see. Are we 5-4? Okay, have I done 5-4? Okay, I've just given a few of them. So the 5-4 will be the maximum, and 4-5 will be 4-5 will be 0. So I see that 4-5 is 0 because they are at the farthest position. Okay, so this is how you can find out the fuzzy preference relations RV from the user preference ordering given by the sequence vector 5, 1, 6, 3, 2, 4. Right? Now, another exercise could be in a corpus of 150 documents, the number of documents that are relevant to a query queue are 35. While actually retrieving the results for this query queue, the number of documents retrieved are 65, out of which only 25 are relevant. Find out recall and precision. So very clearly, recall is this 25 out of 35. Total relevant were 35, but only 25 relevant were retrieved. So this comes out to be 25 out of 35. Precision is 25 relevant documents retrieved out of a total of documents, 65 documents retrieved. So this gives us a practice about calculating recall and precision. Again, suppose I have to find out as many as possible. 1, 2, 3, 4, 5, 6. I 0 to 6, I by 6, 0 to 6 by 6, which is 1. And then Qi by M is 0, 0, 0. I'm talking about as many as possible, right? So as many as possible, we all know starts from 0.5 and it saturates at 1 when this goes to 1. Right? So for all values less than 1, it will be 0, 0, 0. So this far it will be 0, 0, 0. Qi by M is assumed 0 anyway. Now from here on, I'm into the linear range. So this is the linear value 0.334, right? And this will be 0.667 and this will be 1 because I've reached 1. So now this minus this will be W1, this minus this will be W2, W3, W4, W5, W6. This will be found out 0.334 minus this. 0.667 minus this, 1 minus this, right? Now finding out OWA, since first 3 weights are 0, so I've kept all 3 values as 0. Now 0.334 into fourth largest. It will not be largest because largest, second largest, third largest are zeros multiplied by zeros, right? So fourth largest. So we see that largest is this one, second largest is this one, third largest is this one. So fourth largest 0.5. And then fifth largest, which is 0.2. Okay. And then W6 into the smallest, which is 0.1. When you calculate it, it should come out to be 0.267. So these were some of the practice questions for today. Now let us move on to the next topic, user feedback based enhancement in web search quality. The idea is that in order to find out the search quality measure, we had tapped onto the implicit feedback from the users. We had been watching the actions of the user, like what sequence the documents were clicked in, how much time is spent, whether we printed, whether we bookmarked, email, copied and pasted, and so on, right? So once we are using those implicit user feedback for finding out the true ranking in order to calculate the search quality measure or the fuzzy search quality measure, why can't we use that implicit feedback to have a search engine of our own by learning from the user feedback? Right? So user feedback based enhancement in web search quality is what we are going to see next. So these are the major steps. This is our relevance matrix. Let us initialize with some arbitrary values, random values, equal values, whatever. Now for every query queue, we have to sort the documents based on that query and this. Now display these documents. Display these documents before the user. Collect the feedback vector, VTP, SBEC, all the 7 components or more if you have taken them. Now, based on this feedback, we have to update the matrix R using the feedback vector F. So this is the major step, outline of major steps for web search by feedback learning. We will see in detail how can we do it. Our search engine maintains a database of document URLs indexed by the keywords in the documents. So let RDK be a variable in the interval 0, 1, indicating the relevance of document D for the keyword key K and vice versa. Let R be a matrix of all such relevance indices. A query queue will contain a number of keywords combined using operators such as and, or, and not, as we have seen earlier. The relevance matrix R is used by the search engine to select the best documents for the query queue, right? So basically we are having a large matrix, not necessarily a square matrix. It is a large matrix where you may have documents over here, D1, D2, so on up till DM, and you have the keywords K1, K2, and so on up till Kn, so that this is an n by n matrix. So any value RDK over here, okay, so this will be the relevance of this document, of this keyword in this document, okay, of the the relevance of the kth keyword into the dth document, right? So whenever there is a query, for example, there is a single word query, K5 for instance, what I'll do, I'll take the column corresponding to K5. I'll simply sort it in a descending manner, and whatever be the result, I place before the user, because the most relevant will be the largest value. So that document should come at top. Second largest is second most relevant, that should come second. So this was about single keyword queries. 2 keywords joined by say and K5 and K7. What I'll do, I'll take these 2 columns K1 and K5 and K7. I'll take a min of these 2 values because this is K5 and K7. So minimum of these 2 values, minimum of these 2 values, minimum of these 2 values. So I'll get 1 column vector again, descending sort, and whatever be the result presented before the user in a descending manner, those documents in a descending manner. Had it been K5 or K7, combine or K7, then in that case, I'll take the max of the 2 values, max of these 2 values here, max of these 2 corresponding values here, max of these 2 corresponding values here, do a descending sort, and based on the decreasing values, present those documents before the user. So this RDK matrix. Similarly, for not queries, if there is a not query, I'll take a 1 minus before doing min, max, whatever, right? So that is how you can have Boolean queries evaluated for relevance using our index matrix RD or R. Okay, RDK will be the RDKth value. So identify the columns corresponding to the keywords in the query and combine them correspondingly through fuzzy and, fuzzy or, and fuzzy not. For our simple case, fuzzy AND will be min, fuzzy OR will be max, and fuzzy NOT will be 1 minus. Results in a single column of real values that represents the query relevance vector QR. The elements QRD of this vector indicates the relevance of the document D for the given query. A sorted list of documents in a reverse manner, that means a decreasing sort, corresponding to the descending values in the vector QR would form the search result to the given query Q. Right? So somehow I have to get hold of the relevance matrix R. Okay. There could be other queries also. For example, linguistic operator, query formulation using linguistic operators. Most of the keywords, or at least half of the keywords, or as many as possible keywords, etc. So the kth element of the query relevance vector QR may be obtained as follows. Suppose TI1, TI2, TIN. So I'll take all these values. I'll do most or at least half of these values. Right? For example, this is the relevance matrix. So I'll take all these corresponding values and I'll do at least half or as many as possible for them. Similarly, these values, at least half as many possible for them. So it depends how many keywords I want to keep in the linguistic operator. So this will be the ordered weighted averaging linguistic operator queries. How does this query help? In the previous case, in the case of Boolean queries, I have to form the connectives. I have to decide whether I'm looking for analog and digital, or analog or digital, or I'm looking analog and digital computing, or and not computing. So the onus is on me to decide what logical connective I'm going to have. Using linguistic operator, I just have the collection of keywords. I'll say I'm looking for documents which contains as many as possible of these documents, or at least half of these documents, or most of these keywords, right? So I can calculate using the linguistic operator. So that may be one of the advanced queries that we may look into. Likewise, I may have weighted logical operators. I want to assign weights, analog to a weight 0.8, computing to a weight 0.4, and systems to a weight 0.3. So analog 0.8 and computing 0.4 or systems 0.3. So these two are odd and this is ANDed. So the user wishes to give an importance weight of 8 by 15 to the term analog, 4 by 15 to the term computing, and 3 by 15 to the term systems. So the user can assign weights. So the kth element of the query relevance vector QR may be obtained as follows, right? Max and min. Why max and min? Because I'm doing the fuzzy ANDing and ORing. And then before I do the AND or whatever the case may be, I'll multiply these values by corresponding weight. So wherever I have K1 as analog, I'll multiply all of them with 0.8. If this is computing, I'll multiply all of them with 0.4. If this is systems, I'll multiply all of them with 0.3. And then I do the corresponding fuzzy ANDing and ORing. So this could be query formulation using weighted logical operators. Okay. So this is how I can make use of the relevance. Now, importance of a document. When feedback recovery is complete, we compute the importance weight sigma G for each document J. You remember this? We used to have this when we were finding out the search quality measure, not the fuzzy search quality, but the simple search quality measure. So this is how we were calculating the document importance weight based on the implicit feedback from the user. Okay. So up till this point, formulating results. If I take you here, yes. Display documents. Now collect the feedback, right? And this then update matrix. So I'm talking about updation of matrix now. Yeah. Okay. So this is how we used to calculate the document importance weight. We have discussed this already, so I'm not devoting much time to it. For the sake of completeness, I have repeated this slide here. Now, learning from the user feedback, we need to boost up the weights of the documents being consistently picked up by the users and penalize those which are being mostly ignored by the users. So let us assume initially that the query queue is constituted by a single keyword, say K. So this will be my learning formula. The I plus 1th iteration of RDKth value will be the ith iteration of RDK plus mu times the document importance weight and 1 plus mu sigma d, which is the normalization weight, right? So this learning formula is a very good formula. This formula is a very good formula. I'll prove in the subsequent 2 slides. But let us first see how this formula helps us. See, what it is doing is, it is improving on the I plus 1th iteration based on the document importance weight sigma d. Now this mu is the learning rate. Okay. So basically machine learning is taking place and this mu is the learning weight. Why is this weight provided? If you don't provide it, you cannot control the rate of learning. So the maximum learning that we can have, which means the value of mu could be 1, right? So entire sigma d will get added to the ith iteration of RDK. But we may want to vary this learning weight. So accordingly, I can choose the values of mu between 0 and 0.1. For no learning, I can keep it 0. But for intermediate learning, I can have any value between 0 and 1. So the idea is that if you want to have a fine learning, then in that case, the value of mu should be lesser. But if you want to have coarse learning, you want to have major learning steps or bigger learning steps, then this mu could be 0.8, 0.7, 0.9, something like that. Okay. So this is how it is happening. Now 1 plus mu sigma d is basically the normalization factor, which ensures that the I plus 1th value remains bounded by 1. That remains bounded by 1. Okay. So what we will do is that we will prove that using this formula, a couple of things happen. I plus 1th iteration is always an improvement over ith iteration, which means learning is taking place, smaller or bigger, whatever, that depends on mu. And secondly, RDK, any iteration for any value of I, the value of RDK remains bounded by 1. Okay, so this is something that we will see on the next turn. So we will stop here because we've taken a few tutorial questions also, and then we have introduced this new concept of web search by feedback learning. So I don't want to get into the theorem aspect today. On the next turn, in the next lecture, we will take up a theorem to prove these points, that I plus 1th iteration is always an improvement over ith iteration, and I plus 1th iteration always remains bounded by 1. So we will stop here.